I'm Norman here. I'm a lecturer in the Department of Computer Science. I play with data. So a few years ago, I was looking for collaborators. I went around looking for people to work with. I said I wanted to do healthcare, but I don't know what I want to do exactly. So somebody pointed me to Simon, and he then introduced me to some problem in the chronic kidney disease, which is one of the common long-term conditions. And from there onwards, I work a lot more with different kinds of conditions, and diabetes and all other types. But my approach is always using machine learning techniques. And anyone in the floor doing statistics? Yeah, got one or a few people. And presumably your background, how many of you consider yourself technical? Can you show hand? Right, okay. So can I assume that most of them are non-technical? So that means no equations in my presentation, right? Okay, I got one simple one. Okay, so but I just got one equation, but that's not the point. The point is that the main message that I want to put forward is that machine learning can be used to model a lot of problems, especially in healthcare where there are lots of data. And I will show you some of the case studies here below. And let's look at some of the common machine learning tasks. Okay, we have supervised learning, and we also have unsupervised learning. In the supervised learning, the most common model is regression. And the terminology used is below here. We have a dependent variable, independent variables, and you have the dependent variables. Yeah, okay. And sometimes we call the independent variables predictor variables. Okay. Whereas in classification, we try to look at develop a model that distinguish typically two classes, but that can be more. Okay. So we have variable 1 and variable 2, and the terminology used here is that variable 1 and 2 are just live in a feature space. Okay. And typically, we work with a high-dimensional feature space. For instance, a risk model. So if you take a risk of cardiovascular disease, that's a risk model. Okay, and the model will take a number of variables, and the number of variables that will be the features that we are looking at. Okay, and the output of the model, that is the posterior probability of a patient will have cardiovascular disease or not. Okay, so that is the typical classification task. We also have unsupervised learning. An example here is clustering. So in a two-dimensional space, on the right-hand side, you have data points. So this is two-dimensional data. Initially, the data has no labeling. And after the training, we take a clustering method. And the output of them is some clusters. So some yellow dots, green dots, and so on. Okay, that represent different structures in the data. I'm going to show you with real case examples of regression, classification, and clustering. Okay, so I'm going to skip that. In general, there are a lot more algorithms and machine learning tasks out there, but I just pick a few just to make my point clear that there are lots of algorithms out there, methods and algorithms out there that can be used. Okay. Now, let's look at supervised workflow. So, if you think about how is it possible that we use past data to predict future data, yeah, we call that prediction. Okay. How do we actually build models that predict the future? This is not like asking an oracle. Asking what will I be tomorrow, what happened to me. There's no trick. In machine learning, everything is about data. Okay? And so you have the training data, which is the past data, whereas the test data is the future data. Typically, we do not have the future data yet. Okay? So then, let's look at the training data, and the data will have the labeling. So in this case, there could be patients that have cardiovascular disease or don't have cardiovascular disease, for instance. Okay, and then we separate the data from the label. We develop a model using an algorithm, supervised training, and that will come, and the output of this is a model. Okay. Once the model is ready, so the model is nothing but a statistical, a model is a function that takes on a particular forms with some parameters. Okay. And after that, you take the model, give the test data to the model. This is the future data, and then it will give you the model, the predicted level or the risk score. Okay. And then we compare with the actual ground truth results when we have that. So typically, if you do a cohort study, so after some period of time, you would have the results, the actual people you are following after a few years down the line, and you can tell whether a model is correct or not. Okay, and then from there you can actually measure the performance of the system. Okay, that's how you measure the performance of the model. Okay, so that is a very simple introduction of machine learning with some example tasks. Okay, now let's look at some real clinical case studies here. So we're visualizing high-dimensional data. If we are running out of time, I don't have to go through all the cases, but I just want to make my point clear. Okay, here's an example. So I took effectively what Simon mentioned about his data set. This data is a quick study data set. It's a quality improvement in chronic kidney disease. Okay. We're also working on the RCGP data set that Simon is going to give us soon. And there are a couple of other data sets. This particular data set, we have what we call in the x-axis clinical space, a concept space. These are the clinical codes. And Simon mentioned about diagnosis, treatments, drugs, procedure, biomedical measurements. So this is the number of variables we have along the x-axis. Okay. Whereas on the y-axis, we have number of patients. So typically, they can go to millions. But this is just an example here. 10,000 patients. It's a toy example. And if the red point shows that it has data, so and the blue one is empty. So what do you observe here? If you look carefully, and below you have the distributions. Okay, the blue one. So if we have 10,000 patients, then the count of it will be up to 10,000, right? You can see on this one. Okay, so if I line the data by the density, how likely they're populated, you can see that the data quickly reduces. So as you can see, the data is most of the time empty. It's very sparse. Okay, and I'll draw your attention to a face image. So what is it that a face image has to do with patient records? Can you guess that? It's going to be quite challenging. It'll be a leap of faith to answer that kind of question. What's the difference? What's the common thing between a face image and a patient record? Identity, that's a good one, but that's not the point I wanted to make. It's a good attempt. Sorry? Distinguishing features. That is closer to the point I want to make. Yes. Any more attempts? Yes, correct. You do not need all the data. That's the correct point. And in the mathematical concept, we call it compact dimension. What is the intrinsic dimension of the data? Face is 100 by 100 pixels. That's 10,000 pixels. But if you look at the patient record, that's 11,000 records, variable, which means that they are they are about roughly comparable in terms of number of dimensions. But the intrinsic dimensions of the data is much lower. So what's an intrinsic dimension? We come back to that question. But basically, intrinsic dimension is the how can we compact the data such that we can represent them in much fewer variables in a layman term. Okay, so I took the data if you take Chinese medicine, you know you have to brew the essence and then get the essence out of the medication, yeah? And normally it tastes quite bad. Okay, and what I'm trying to do is to brew the data down to 2 dimensions, and it's called dimensional reduction. So I think that Chinese medicine could be a good analogy. And what left over is the essence, is the intrinsic dimension of the data. Hopefully it's an intrinsic dimension, because we don't know what really is there in the data, right? Okay. Now, and the algorithm I took is T-stochastic neighborhood embedding. It's a dimension reduction algorithm, and there are quite a lot of algorithms out there. We always have to tune the parameters and find the best parameters that would suit our problem. So there's a lot of experimental science going on here. But the key message is that when we reduce the data down to 2 dimensions, we begin to see something that's emerging. This is the patterns in the data. And I start clustering the data. So one point will be one patient record, okay? Now come back to the question, though. What's the similarity between a patient record and a face image? On the right-hand side, we took the algorithm, applied to images, and you can see the people of the same faces cluster together, okay? On the left-hand side, you see the patient records. Then you can imagine that the records of the same characteristics are grouped together, okay? What is interesting about this data set is that nephrologists or clinical consultants, what they normally do is cluster patients by their stage of the disease. So you are CKD stage 1, 2, 3, 4, or 5. If you are in stage 4 or 5, that requires renal transplant. So could be a very bad, it's one of the worst outcome. Okay, but what we're trying to say here is that rather than categorizing the patients by their outcome, why don't look at their trajectory, their history. So the point I want to make here is that you can actually cluster the patient by looking at their trajectories, which is encapsulated in the patient record. Okay. What I found is that there are actually 60 clusters in the data. So that's quite interesting because if I know a patient in front of me belongs to one category, one particular profile there, one of the dots there, one of the 60 profiles, then perhaps I can group them together and observe how they actually go on to develop the kidney conditions. Maybe the outcome is different, and I can tell you that some of the clusters, some of the patients are younger, older, and they're definitely this cluster is very different from the other cluster. So there are a lot of potential here, and so I'm actually looking at this at the moment through my project with Simon, funded by the Medical Research Council. Okay, so that's a big question we are asking here, and here is just a demo of what's in the data, in much granularity here. And you can see these are they're very distinctive. They're certainly very different from each other. So trying to understand the data itself is a challenge because we have lots of clinical variables to begin with. Okay? So that's the point I want to make about clustering here. Let's come back to type 1 versus type 2 diabetic, okay? So again, this is a classification problem. Anybody controlling the time? So when I speak, it doesn't mean start. All right, okay, that's fine. I go ahead. Okay. So this is the second case study. First of all, I'd like to know that I didn't know much about diabetic apart from family history. You know, we know a little bit of diabetic, but not much. I don't know much. And I actually learned about diabetes from the algorithm itself. Okay, and here's the exercise for you to do it later on. Okay, so in the 10,000 patients, some of them have type 1 diabetes, some of them have type 2. This is a Venn diagram. The blue one is the type 1 diabetes patient, and the yellow one is the type 2. So obviously much larger in population. Yeah, so that makes sense. And the red one here is 271 of them. It's when I observe the records, it shows that a tiny portion of them has both type 1 and type 2 diabetes. Any one of you are GPs or clinical consultants here? Can I raise your hand? No? Simon? Okay. How many people have type 1 and type 2 diabetes at the same time? Do you know? How many, Simon? How many patients have type 1 and type 2 diabetes at the same time? Okay, so there's something wrong in the database. There might be miscoding. So that highlights an important issue. A lot of real data we work with, they're very noisy. There might be errors. There might be sampling bias. And so we need to correct for those problems. Okay? So it's a very noisy data. Not only they are big, but they are noisy. Okay? Possibly miscoded. Okay? So let's use an algorithm to clean the data up. Okay? To do some cleaning using the algorithm. And remember, the algorithm doesn't know anything about diabetes, to begin with. Okay? So let's call that it's type 1, and in the data set, there are 5 byte records. So if you look at clinical codes, C10E means type 1 diabetes, and C10F means type 2 diabetes. Okay? So give the algorithm some simple labeling, and then let's train the model, and later on use the model to clean the data in the middle, the red one. Okay? Where they intersect each other. Okay? So we take the model, positive records, negative records, clean the data up, build the model, train a classifier, so you get the first model, So you do the training, you get the first model, and after that, we give the feedback to the clinicians. In this case, we use the training data as a way to see that if the data is correct. Okay, but typically we give the feedback to the clinicians to check whether the features found are reasonable. If not, we remove some samples and repeat the process to get a second model. Okay, so then you iterate in the process that way. Okay. One thing about training a machine learning algorithm is there is something called overfitting and underfitting. Have you heard of the term before? Have a show of hands? Okay. Yes. So you guys are doing statistics and machine learning, so you know a little bit. For the majority of you, I would assume that you don't know much. Okay. The point is not, I'm not going into the details, but to say that there's an equation that you can see below. There's an error they want to minimize, and that error is composed of 2 terms. One is the model error, and the other one is the model complexity. And we need to tune the model complexity. In fact, we want to penalize the model, complex model, but at the same time minimize the entire error function. Okay, this concept is called regularization. Okay, and there are a lot of algorithms out there to do that already. And the one we use is regularized logistic regression. And what the model does is that as we use more and more complex model, by tuning the lambda parameters, we also see the coefficients of the variable growth. So if you are here, there are only one variable with one coefficient. So as we increase the lambda parameter, we'll see more and more variables are set to some values. Okay, and you can, if you are on the right hand side here, there are a lot of variables with values. Okay, so the model is very complex. So moving to the right is a complex model. Going to the left is a simple model. And here, what it shows in the diagram here is called the error of function. And high means large error, small means small error. Okay. So as we tune the lambda, we see the error is going down because and there's a sweet spot. Okay. To the left of the sweet spot, you are underfitting the data. On the right hand side of the sweet spot, you are overfitting the data. So, and the key point I want to highlight here is that you can use any algorithms out there, but don't forget to tune your model complexity. Okay? So that is the trick of machine learning, and we do that exercise all the time. When we got a piece of data, we have to tune it carefully. Okay? So there's no magic. There's a lot of hard work going on to check the model is correct. Okay? And so now we look at the data. You remember the yellow one is the type 2 diabetes, and the type 1 diabetes is the small one. So you see the index are different. This is up to 8,000. This is up to 200. So if I sort them by their posterior probability, so if the probability is high, posterior probability is high, that means that's type 1 diabetic patients. And if the posterior probability is close to 0, that's type 2 diabetic patient. And what we show is that this data set is presumably type 1 diabetic patient, but a large portion of them has very low posterior probability. Okay? If all the data is really true, really true to what they say, then they should have all type 1 diabetes. I would see blue everywhere. Yeah? Because the posterior probability should be picking everywhere in the training data set. But this is not the case. What is it telling us here? Yeah. maybe among the data, patient records that I'm observing, even though they are been labeled as type 1, probably a portion of them is actually type 2 diabetic patient. Okay? And the type 2 diabetic patient, I would have thought that the posterior probability should be low everywhere, but then there is a small portion of patients that has very high posterior probability. So that means that indicates type 1 diabetic patients that's present in the type 2 labeled patients records that's been labeled type 2 diabetes. Is that possible? You know, the miscoding and error happens all the time. So, and machine learning algorithms possibly can pick that up. So what we do is clean the data set, define a threshold, and say that let's retain the data that we are confident with. That will be type 1 diabetic patient. That will be whatever here will be type 2 because the posterior probability is low. Okay, let's train the model, a second round, and then we get a different model. Now what we do is, after we got the model, we tested it in the middle section, the middle data set where there's ambiguity whether their patients are records of type 1 or type 2, yeah? So there are about 270 patients there. So what I observe is that if we align the data by their posterior probabilities, we can see that where we can indeed clean the data with some confidence. On the left-hand side, these are certainly type 2 diabetic patients. On the right-hand side, type 1, leaving the patients in the middle, about 50 of them, to be verified manually. Okay? So what have we learned from here? So we learned that machine learning algorithms, using some simple clue, it can actually distinguish type 1 and type 2 diabetics without having the domain knowledge. Now, when I look at the coefficients, this is what is being printed out by the variables in Model 1 and Model 2. Can you read at the back there? This is a 5-byte record representation, and this is the coefficients that is that's given by the model after training. Okay. So let's look at some of I have annotated the output here. So if you look at the subcutaneous injection, so F143, it's Novorapid pen filled with cartridge 3 milliliter, and there is a pre-filled pen and so on. So Simon can confirm that those are patients that inject insulin through some sort of pre-filled pen and other device, right? We call subcutaneous injection. Okay. So if patients are taking insulin through subcutaneous injection, they're more likely to be type 1 diabetic. Type 2?
There'll be a bigger number.
Yes.
Only 10% of people got type 1.
Yes.
There'll be more people with type 2 who have insulin type 1.
Yes.
But the proportion is obviously much lower.
The proportion of type 1 is much lower.
So the proportion of type 1, but everyone with type 1 needs insulin for survival.
They need insulin for survival. But does it matter the way you take the insulin injection? No. Okay. What the model is telling us is that is to be verified. Okay. And it's always debatable. That by insulin injection, that's type 1 diabetes. Okay. And type 1 diabetes takes oral anti-diabetic drug. Exactly the other way around. Sorry, it's actually type 2. I'm mislabeling. It's type 2 because the coefficient says negative. So I made a mistake. The algorithm didn't. I forgot to say negative coefficient means supporting type 2. Positive coefficient means supporting type 1 diabetic patient. Okay. I made a mistake. So the model is it's telling me something. Okay. Blindness is the leading complication of diabetic. So that's general, whether it's type 1, type 2. In this case, the coefficient is positive, so it's more inclined to type 1 than to type 2. Okay. Then there's a use of statin, and I look up on the internet some literature. It says that prescribing statins can reduce rates of cardiovascular disease in people with diabetes. Okay. So I learned something from there. Metformin is common for type 2 diabetes, so it's a drug. And then I highlight something here. So there is some clinical codes that implies the ethnicity. So there is a main spoken language is Urdu. It's more inclined to type 2 diabetic patients. So if you, does it mean that if you speak Urdu, you get type 2 diabetes? No, right? So you know that the model can suffer from sampling bias. Okay? And the key message here is that I know that model is telling me something, and I probably learned something from the model, but I know that it may suffer from sampling bias as well. So always work with the experts to verify the model. Okay? So I give you some example of clustering, classification. I guess I can go to conclusions, but in the interest of time. Okay? So here's my some of the conclusions and my opinions on where machine learning can be used. It can be used to predict model, to discover concepts, to distinguish data from noise. There's a huge amount of opportunities here due to large memory and computer power and ever more powerful algorithms nowadays. But however, there are lots of challenges. Modeling life course data is quite a problem because something that happened at the beginning of the life course of the person may affect that person later on in life. Okay, so that kind of modeling is quite challenging. The causal effect, where the effect is deferred over a period of time. Sampling bias is another. And finally, we want to look at combining machine learning and human experts together. So that's some of my thinking behind what I've done here. To conclude that talk, I just want to leave you with a diagram here showing that if I know where the patient profiles are, perhaps one day I could eventually look at how the patient gets to that worst stage of the disease through different pathways. So potentially you can start visualizing the pathway. Thank you very much.